we're going to extend our bag of tricks to a larger class of integrals. We're going to look at something called integration by trigonometric substitution. So this is going to be another way of doing substitution to simplify your integral. But this way is going to be a little less obvious than we've done so far. So let me first just maybe give you a background which will motivate this substitution method. So recall we got our trig functions from the unit circle. And remember the way we actually defined sine and cosine was by taking a ray originating from the origin and heading out and intersecting the unit circle. And whatever point you got, right, well, it has some coordinates, x and y, whatever they are. And, well, we defined those coordinates in terms of the angle that you get between the x-axis and this ray. And whatever the x-coordinate of that point is, you call the cosine of that angle. And the y-coordinate you call the sine of that angle. And then we showed that this actually gave you something which, at least between 0 and 90 degrees, was equivalent to how you define cosine and sine for a right triangle. But from this point of view, things are very easy because, for instance, you know the equation of that circle. It's x squared plus y squared equals 1. Which means every point on that circle satisfies that equation, which means, for instance, that cosine squared plus sine squared is equal to 1. So this gives a very short proof of that fact. Very easy to remember. And, well, if you fiddle around with this formula, you can get another nice formula that relates tangent and secant, or at least their squares. Yeah. Which really just comes from this first one. All right, so we're going to use these two formulas to build a substitution method. So, for instance, if we take this equation, then we know, for instance, that say cosine squared is 1 minus sine squared. Yeah. On the other hand, we could do the same thing with this sort of equation, right? Y squared equals 1 minus x squared. Or, if you like, y equals the square root of 1 minus x squared. Of course, I'm omitting, this should be plus minus. Right? But let me just look at the positive one for now. So, and I could also, like I said, have the same thing over here. I could write 1 minus sine squared theta equals cosine squared theta. And, well, square root of 1 minus sine squared theta is cosine of theta. Okay. Or again, we just are taking the positive square root. Okay, so what this tells us is that if we can find an expression like this in our integral, it might be useful to turn it into this sort of an expression. Because it might be, difficult to integrate something like this, but we know how to integrate something like cosine. Okay, so this is where we're coming from. This is our motivation. And what we're going to do is try to figure out what to do with 3 different expressions. So the first one is going to be expressions of the form the square root of a squared minus x squared. The second one will be expressions of the form a squared plus x squared. And the last one will be expressions of the form x squared minus a squared. And in all these cases, a is greater than 0. All right, so we're going to try to figure out a good substitution. So let's look at this first case. We have a squared minus x squared, and we take the square root. Well, when I had a 1 here, I knew what to do, but with an a, things aren't that much more difficult. I'm going to try the following substitution. Right? Over here, we replaced x with sine of theta. Right? So here, well, with this extra a around, I'm going to replace it with a sine of theta. Okay, now let's see how that plays out. If I make that substitution, then this square root becomes the square root of a squared minus a squared sine squared theta. X squared is now a squared sine squared theta. If I factor out an a squared, then I get a squared times 1 minus sine squared, which gets me back to this nice case. This breaks up, square root of a squared would be a, and then I get the square root of, well, 1 minus sine squared is cosine squared. And of course, this becomes a cosine theta. Okay, so this is very weird. Why is this weird? Well, first, when we've done substitution in the past, we've always done, okay, I have some nasty expression, and now I say let u equal some part of the expression. In this case, we're not going to do that. We're not going to say let u equal. We're actually going to do it the other way around. We're going to say let x, right, replace x with an expression. Okay, and of course, we're not using u, we're using theta as well. When you talk about trig functions, you like to use these Greek letters. It's all fine. So the nice thing is, if you make this substitution, you then reduce this nasty square root into a very simple form. So let's see how this plays out in a real problem. Let's look at the integral of x squared over the square root of 9 minus x squared dx. Okay, so my first instinct on all these is, try to do some sort of nice substitution. And you might think first, try u equals 9 minus x squared. If you do that, okay, then the du will be minus 2x, and you're not going to be able to cancel all these. So you run into trouble already. Okay, but it is in this nice form, square root of 9 minus x squared, right? It looks just like this form. What's a in this case? Well, a, right? A squared is 9, so a is 3, right? Why not minus 3? We always assume in our case that we make a be greater than 3. Okay? So we make the substitution. X equals 3 sine of theta. Now, if we do that,
wait, why is it 3 sine of theta?
This is what we are hypothesizing will be a useful substitution.
Okay.
So for integrals of this type, right, where you have a square root of a squared minus x squared, we're going to try the substitution x equals a sine of theta. Be a sine of theta? Where does it come from? It comes from here. All right. We saw that you can mimic this sort of situation with the sines and cosines. Right? And so we just try to generalize it a little bit. Right? Instead of a 1, we have an a, or an a squared. But other than that, we're doing the same thing. We're saying, if you put in this sine squared, you can really simplify this expression so that you don't have to have any square roots or nastiness. You just get a nice cosine. So this is the motivation for it. Okay, so let's try to use this substitution to transform this into something that just involves thetas. So we know x is 3 sine theta, so x squared just becomes 9 sine squared theta. Okay, and the square root of 9 minus x squared, what does that become? You could try to think real hard to figure it out. Or you could say, wait, that's just what we computed up here. If I put in x equals 3 sine theta in this expression, I get out 3 cosine theta. That's exactly what this derivation did. It says, I have that expression. I can always replace it now with my 3 cosine theta. Now I have to worry about this dx. If x equals 3 sine theta, then what does dx equal? Three cosine theta d theta. Excellent. Okay, so I have to throw that in. 3 cosine theta d theta. This is not so bad. Okay, look what happens. 3 cosines cancel. You can pull that 9 out. And I've reduced it to an integral that we already know how to solve, namely sine squared. And if I remember this correctly, okay, there's going to be a half, and then x, or theta, here, theta minus sine theta cosine theta plus a constant. Okay, so we've almost finished. We got rid of the integral. The only thing left to do is, I gave you a problem in terms of x, and we have an answer in terms of theta, so we have to throw everything back into our x forms. So, let's see here. Mind you, this whole step here, right, this is just a formula that we derived in class, so you could look up the formula if you don't remember it. Don't worry about that. Okay, so theta, how can I write theta? If I know that x is 3 sine of theta, then what is theta equal to? Let's see. So I divide by 3, and I get sine of theta equals x over 3. And then I take arc sine, right, which kills the sine function. So I get arc sine of x over 3. Okay, that's my theta. Divide by 3, and then take arc sine, and that'll isolate theta. All right. Then I have minus sine of theta. How can I isolate sine of theta? X over 3. Okay. Now what about cosine of theta? This is dx over 3, but, well, actually it's dx by d theta, all right, times a third. Of course, we don't really want to introduce the dx d theta in again if we don't have to, especially since it will just resolve to be something trivial. But we actually already know something. 3 cosine of theta is the square root of 9 minus x squared. So if you divide by 3, cosine of theta is the square root of 9 minus x squared divided by 3. That's what the way we replaced the square root of 9 minus x squared was with 3 cosine theta. So if you divide by 3, you get back cosine theta. And, well, I just can't help myself. There's a couple of 3's down there that multiply to be 9. Not 9, it should cancel them. So this will be 9 halves arc sine x over 3 minus x root 9 minus x squared over 2. Okay. just distributed this 9/2 in. It's a fun cancellation. Wow, Garrett, you look really irritated.
Yeah, I'm trying to, wait, how did you get from the 9 integral sine squared theta d theta down to,
Yeah, so I'm using what we did last week sometime, which I don't expect you to have memorized, and it's rather frustrating that I have. This is just, we worked this out using integration by parts. So that's just a formula which you either can work out on the fly or you can memorize. I had no choice. You see it enough and you memorize it. Okay, so that's just me helping you go through it faster, but yeah, it's a step to do. Let's try another one. So let me summarize over here. When you have an expression of this type, the trig substitution you want to make is x equals a sine of theta. And when you make that substitution, then this is going to turn into a cosine of theta. That's what all this work told us. So let's try this expression. Again, maybe the most natural idea for substitution is to say u equals 1 minus x squared. Okay. But then when we differentiate, we get minus 2x, and this x is on the wrong side of the line to cancel out. So that's not going to work so nicely. If this x was up top, it'd be a good substitution. Okay, so but we do have this nice form, right? The a squared minus x squared under square root. So we try that substitution. So here a is 1, so we just get 1 sine of theta. Okay. So this is going to become, well, right, we said over here, when you make this substitution, right, then that square root expression will turn into, well, in this case, it'll be 1 cosine of theta. So the top just becomes cosine of theta. And the bottom becomes sine of theta. So let's see what happens to dx. So if x is sine theta, dx is cosine theta d theta. So we get time, so the dx becomes cosine theta. D theta. Or if you like, cosine squared over sine. All right, any ideas how to simplify this expression? Cos squared into 1 minus sine squared. Yeah, let's try it. Okay. This doesn't work. It's your fault. So we replace cosine squared with 1 minus sine squared. And I suppose you probably want to break this up into 2 different fractions. So 1 over sine. What's 1 over sine?
Cosecant.
Cosecant. Minus sine squared over sine is just sine.
Interesting.
And this one we already know. Right? That's just going to be minus cosine of theta. So, like, how is it that we got all this way and we don't know how to integrate cosine?
Sure we do.
Do it?
Well, Edgar taught us.
Oh, did he?
I kid.
All right. We're going to come back to this one. We'll come back to this one. I think we should formally at least get down the answers to all of these basic ones that we should know. So we'll come back to this. Okay, good. But the nice thing is that there will be an answer for this one. And we've done all the hard work already. Okay. So the hard work is identifying this to be integration by trig substitution problem. Make the right substitution, and then fiddle around with it. Okay, so let's see. Let's just see what would happen if
Go on.
if you tried it a different way. If you'd broken this up, or not broken, just left it like this, cosine over sine times cosine. Would that have helped you any? Right? Well, cosine over sine is cotangent times cosine. I'm not saying this is a good way to do it. I'm just saying you might have also seen it this way. The problem here is you really don't know. I mean, if this was a cosecant, then we'd be in okay shape, right? But with a cosine, we're just not so sure. So this isn't so nice a form. So this is really the better way to go. When you see cosine squareds and sine, you know, this is a good hint. Yeah, probably make that a 1 minus sine squared. Okay, so that's the way it works. Let's try this second one. Say we're in this case. We have an integral that has a square root of a squared plus x squared. Now, I want to utilize this formula that we wrote down. Tangent squared plus 1 is secant squared. So what would be, if I want to utilize this formula, what do you think would be a good substitution for x? Tangent, good start. If it was 1 plus x squared, it would be perfect. But if it's a squared plus x squared, what do you think I should toss in front?
1. What?
If it's really a squared, not a 1 squared.
A.
Throw an a up there, right? It worked last time. And why did it work? Well, it worked because when you square x, you get this a squared, and then you can factor out the a squared, and you're left with 1 plus tangent squared. Then you get your secant squared. Everything works out. Let's do that. Okay, so with this substitution, we get a squared plus a squared tangent squared. If I factor out my a squared, I get 1 plus tangent squared. My 1 plus tangent squared is the secant squared. So I get a secant of theta. So what this says is if I start with an integral with a squared plus x squared, square root, and I make the substitution x equals a tangent of theta, then I can replace in the integral this nasty expression with a secant of theta. see an example. So here it doesn't look right at first because I don't see a square root sign. But that's okay because there is a half power in here, yeah? That's a square root. Now I got this 3 here, but that really just means take the square root and cube everything when you're done, right? So I can still use this method. So I make the substitution, x equals, what's my a here? 2. 4 plus x squared, so I use 2 tangent theta. And what this derivation tells me is that 4 plus x squared square rooted, when I make this substitution, will become 2 secant of theta. If I make the substitution x equals 2 tangent of theta, then the square root of 4 plus x squared will become 2 secant of theta. And then, of course, I have this cube in here to deal with. So I'll just throw that in at the end. Then I got to worry about my dx. Fine. What's dx if x is 2 tangent of theta? Yes, 2 secant squared theta d theta. So I have to toss that up top. Okay, this is not so bad. On the bottom, I have to cube everything, so I get 8 secant cubed. So let's see, 2 over 8 becomes a fourth. I can pull the fourth out. I have a secant squared on the top, a secant cubed on the bottom, so they cancel. And I get 1 over secant, which is, it's what?
Cosine.
Cosine, yeah.
Interesting.
Ah, this is very nice, right? We've taken this brutally, nastily, awfully, disgustingly, I have nowhere to go with this awful integral, and we've turned it into the integral of cosine of theta using this clever substitution. And of course, we know how to integrate cosine. And now all we have to do is figure out what sine of theta is. Well, we can do it this way. If we divide by 2, we get x over 2 equals tangent of theta. Take the arctan. Right? Okay, so that's certainly one way to go. Now, you might recall that we looked at triangles to help solve these sort of problems. So let's do it that way. So if you had a right triangle with angle theta, such that the tangent, right, is x over 2. That would mean the opposite over the adjacent is x over 2. So we could put an x there and a 2 there. And then the hypotenuse of this triangle would be the square root of, well, 4 plus x squared. And so the sine of this angle would then be the opposite over the hypotenuse. So this would become a fourth opposite over hypotenuse, so x over square root of 4 plus x squared plus c. Is that right? Yes. Okay. So this is how we can do it. You guys remember we looked at this sort of thing last term a little bit? This triangle trick? Yeah, okay. So it can be useful. If you don't like that way of thinking about it, here is a slightly different way of thinking about it. Sine of theta this equals sine of theta over cosine of theta times cosine of theta. Agreed? This is multiplying by cosine of theta is the same, however, as dividing by 1 over cosine of theta. Yeah? Which is the same as dividing by, well, what's 1 over cosine of theta?
Secant.
Secant. Or I could write this as tangent theta divided by secant of theta. The tangent of theta is x over 2. And secant of theta is the square root of 4 plus x squared over 2. So if you divide these, you just get x over the square root of 4 plus x squared. Okay, so that's another way you could figure out what sine of theta is. This is probably easier for me, but you could do it. Okay. When do we have till? 50? All right. Let's look at this last one, x squared minus a squared. So I actually want to use this formula again. Right? Only I'm going to move the 1 to the other side. So I'm looking now at expressions of the form the square root of x squared minus a squared. And if I want to use this formula, well, somehow I want to get that to be my x. And my a is going to come from there, and then I can replace things with tangent. So I make x equal to a secant of theta. And when I do that, I get a squared secant squared theta minus a squared. Factor out my a squared again. And I get secant squared theta minus 1. Which is exactly this right-hand side of the formula. So I know I can replace it by tangent squared. And now everything is very nice. You get a tangent of theta. So it's really nice is these two terms. Actually, if I write the x squared first, you can really see the symmetry going on. If you have a plus, then you make it the tangent, and it'll turn into the secant. If you have a minus, you turn it into a secant, and it'll turn into a tangent. Everything just gets flipped, just because of that minus and plus. So let's do a quick example. So now I got my x squared first, right? Minus 16, which is 4 squared. So I use the substitution x equals 4 secant of theta. And this derivation up here tells me that that'll make the square root of x squared minus 16 into 4 tangent of theta. Okay, now x to the 4th, we got to take to the 4th power 4 times secant of theta. Okay, so let's see, 4, 6, what is it? Okay, the first power is 4. Second power is 16. If you square 16, you get 256, so that's got to be the 4th power. 256 secant to the 4th. Okay. Just taking this, right, raised it to the 4th power. Okay, now I need my dx. So what's the derivative of 4 secant of theta? I'll spot you the 4. It's the derivative of secant of theta. Secant tangent, yeah. So, and then there's a d theta, of course. So we have to toss this up too. 4 secant theta, tangent theta, d theta. All right, well, we certainly have a lot to play with. Let's see here. 4 times 4 is 16. 16 over 256 is, of course, 1 over 16. Yeah, 1 over 16. So we'll pull that out. Okay, now I have a tangent and a tangent, which gives me a tangent squared. And I have a secant over 4 secant, so that gives me secant cubed. Okay. Where do I go from here? What's that?
Use that equation.
Oh, the one we had up here? The
Tangent, yeah, whatever it is.
that one? Yeah, we'll give it a shot. Maybe it'll work. Okay, so let's see. We should break this up, of course, into 2 different ones. So the first one, secant squared over secant cubed. So it's 1 over secant, which is cosine. Minus, well, let's see. Let's first a d theta. Minus 1 over secant cubed, which is cosine cubed. Okay. So this one's easy. The integral of cosine is sine. Now this one, well, we actually have a pretty good idea what we would want to do on this. What method would you use to attack cosine cubed?
Substitution.
What would you substitute?
Cosine, but it won't work.
Yeah. What's the other method we have?
Parts.
Parts, right? Remember that's actually how we did yesterday. We did a reduction formula for sine to the m power. Right? We used integration by parts to reduce it. Okay. And actually, you could do the same thing here. If you did integration by parts, right, you can reduce this down quite easily. So let's just quickly see how we would set it up anyway. Man, I didn't fill in the details. to x. So let's say we put our cosine squared over here. That we don't mind differentiating. And our cosine over here. That we don't mind integrating. The derivative here is going to be 2 cosine of x times minus sine of x. And over here we get the integrals sine of x. So this was our u, this is our dv, right? This is du, this is v. So this integral becomes uv, which is sine of x cosine squared of x, minus the integral of v du. So we get plus 2, we have cosine of x sine squared of x dx, which looks horrible, but what am I going to do that sine squared? 1 minus cosine squared. So this is going to become, well, let me see. Let me go into my SC notation. SC squared plus 2 integral of, okay, we're actually going to get 2 integrals. Cosine times 1 and cosine times minus cosine squared. So we just get the integral of 1 times cosine, right, minus the integral of cosine cubed. And if I call my original integral I, then I've actually recovered my original integral I here. So I add it to the other side, and I get 2I equals SC squared plus, well, actually, remember I had 2 of these. I forgot. I have minus 2 of them, so I actually get 3. 3 of those. Okay, so the integral of cosine is sine. So I get 2 s's, and then I threw those i's to the other side.
Why do you have 3 i's?
So remember, here I have 2 times minus I, minus 2i. And then when I add this to the other side, I have 2i plus I is 3i. Okay. Now I divide by 3, and I get a third SC squared plus 2s. I feel like we made maybe an error somewhere. I don't know why I feel that way. Well, you can go home and check the work. Tell me where the error is. Incidentally, it's not an error that I'm worried about as much as there was a simplification. Yes, yes. I'll show you guys the end of this again next time, because there's a faster way to do this than to break it up this way. Yeah. Whose idea was it to break it up like this?
No, this time.
It wasn't your. Are you sure it wasn't you?
I'm sure.
No, it wasn't my idea to break it up that way. No, I'm sure it wasn't me. Who was it? Was it you, Christina?
It was me.
It was Stephanie!
Ah.
Yeah, no, we can simplify this a little bit by turning these into sines and cosines. And we'll simplify the calculation. In any case, this is good practice anyway.